Hi guys. Mm, so back to the session 2. So in this session, before going to start with this session, again back to the discussion whatever we held in our previous session. In the last class, we were discussing about the classification of line. There are three lines as I told: short, medium, and long. So short transmission line, as you know, the length is about 50 km and voltage range is 0 to 20 kilovolts as well. Here the distance is very short, so that capacitance are neglected, so that capacitor effects are small. Only will be considered R and L. C is neglected. In case of medium transmission line, length is 50 to 150 km and voltage level is 20 kV to 100 kV. Here the length is not so short, so that we can consider capacitance taken into account. So we'll be use this capacitance for the calculation purpose. Again, for the long transmission line, length is 150 kilometers and that is more than 150 kilometers and the voltage range is more than 100 kV, and here will be the capacitors are present. As I told, the resistance and inductances are always connected in series, so that we can call it as a series impedance. The capacitance is always connected in parallel, so which will be act as a shunted because it will give path for the leakage flow of excess current, give direction for the leakage current. So as well, representation also were discussed in last class itself. And just look at here, RL C is absent and medium C is present, and we discussed about voltage regulation, sending end voltage and receiving end voltage. Vs minus V are divided by VR into 100, and also these are the formulas we were discussed. And we discussed about transmission efficiency as it is output power to input power. Here output power is the receiving end voltage and input power is sending end voltage. Formula till here we discussed in the last class. Today we will discuss about the short transmission line, that is performance analysis of short transmission line. So here, before going to start with this explanation, look at the circuit diagram once. So here it consists of R and L. L is represented in inductance, that is XL. Impedance we can write as R plus JXL. It is capacitance R minus JXL. Here we will be inductance. Capacitance is absent because the length is short and the load is connected, that is ZL. Voltage across load is VR, that is the receiving end voltage. VS is the sending end voltage, that is generated voltage. And here I use the load current. R is loop resistance, that is you can say it as resistance of both conductors. And XL is loop reactance. VR is receiving end and VS is sending end, both having capacitors or both having power factors, that is VR is having cos phi R and VS is having cos phi S. And just observe here, this is a representation of equivalent circuit of a single phase short transmission line. Three phase is converted into single phase. Whenever we convert the three phase equivalent circuit diagram to a single phase equivalent circuit diagram, 3 points you should remember. The first point is that the voltage across phase should be same, and the second point is current also should be same, and the third point is that very important point, the phase difference between each phase should be 120 degree. Also considered as phase shift is 120 degree apart, then we can say it as balance the circuit. If the circuit is balanced, then we can convert three phase equivalent circuit diagram into single phase equivalent diagram. As I told, just I is load current and ZL is load. Voltage across load is VR, that is receiving end voltage. Voltage across supply is sending end voltage. Resistance and reactance, that is inductive reactance. Coming to this phasor diagram. So the explanation regarding this phasor diagram, you should remember that as you can see here, the reference is I. Okay, look at here. If you want to write VR, just have to apply the KVL. Then you can get VS. Sorry, apply. How can get VS equals to the drop across R is I into R plus I into XL plus VR. That is VS. So if you want to get VS, IR plus I into XL plus VR or else I into ZL. So to draw that, remember here, consider power factor is lagging or else load is inductive load. So the current flows to the load, which is depending on this current is depending on the type of load. If it is inductive load, current lags the voltage. If it is capacitive load, current leads the voltage. If it is resistive, current is in phase with the voltage. That is with respect to VR, if it is considered at the load side. So now current is a reference. So that first we should draw the reference line, that is current I. Then by considering this as inductive load or else the power factor is lagging, so that VR lags I at an angle of phi r. That is a load. VR lags, I lags VR at an angle of phi r because of this inductive load. Yes. So next we should write Vs. So before writing Vs, we should get the equation of Vs. Vs is given by, according to this circuit diagram, by applying KVL. Vs is I into R plus I into XL plus VR. So if you add these three, you can get Vs. So what you are going to do is, you have to write Vs by adding these. So with respect of this O to A, that is with respect of this VR, I can get IR drop. How will be getting IR drop? I know, that is a reference. So draw a line which is parallel to the line I, that is AB line, which represents IR drop. Then draw a line which is perpendicular to the point B, that is IXL. So that I into XL. Now you can see VR plus I into R plus I into XL, you can get Vs. Clear? So this AC is nothing but I into ZL. That is load I into Z. Hope you clear the phasor diagram. If you are having any doubts regarding this, just have to comment me. And angle between I and Vs is phi s. So I'll repeat once. I is a reference. The load is inductive load, so that I lags VR at an angle of phi r. Then you have to write the Vs with the help of equation VR plus IR plus IXL. So IR you are getting, draw a line which is parallel to the I from the point A. So then from the tip of P you have to draw the perpendicular line, you can get I into XL, add VR, IR, IXL, you can get Vs. So giving the namings, so just observe here OV and OD, here OA represents VR and OC represents Vs. Okay. So next write the equation from triangle OEC. Triangle OEC, look at the triangle O and EC. That is the right angle triangle. OEC. Okay, considering this triangle, so apply Pythagoras theorem. By applying Pythagoras theorem, what will get? You get OC square equals to OE square plus EC square. OE square plus EC square. You can get the Pythagoras theorem. So here OC represents what? Here OC is nothing but Vs and OE is nothing but, just see here, this OE. So this OE is given by OD plus DE is nothing but OE. So that we write here OE as OD plus DE whole square. Similarly EC. See here EC. EB plus BC is EC. So that we can write EB plus BC whole square. Then say substitute OC is Vs, OD is nothing but see here OD. So this is velocity component with respect to phi r, so that I can write as VR cos phi r. VR cos phi r is nothing but OD plus DE. This is equilateral, so that AB equals to DE. So AB value is IR, so that DE is also IR. So that VR cos phi r plus IR whole square. Similarly, EB, see here, EB is the same as AD. So that velocity component for AD is VR sin phi r. So that AD equals to, that is B equals to VR sin phi r plus BC. Just look at here, BC is nothing but I into X. Okay, understand. So once you get this, you can rewrite Vs as square root of VR cos phi r plus IR whole square plus VR sin phi r plus I into X whole square. So once you get the sending end voltage, then you have to find, then you can easily get the voltage regulation. Once you know the sending end voltage, and the rule we know that the receiving end voltage is always less than sending end voltage. Once you can get this, you can find Vs minus VR divided by VR into 100. So to get this voltage regulation, I want to get the value of Vs minus VR because I don't know what is VR. So that I define power factor at sending end voltage. So power factor at sending end voltage is nothing but phi s cos phi s. So again you can consider sending end voltage Vs, consider the triangle OCE. So for here phi s. So defined for this rectangular triangle cos phi is given by adjacent side divided by hypotenuse side. Whereas adjacent side is nothing but OE is adjacent side divided by hypotenuse side is OC is nothing but Vs. OC is Vs, OE is nothing but OD plus DE. OD is nothing but again the velocity component VR cos phi r plus DE is nothing but I. So that Vs cos phi r plus IR divided by OC is Vs. So power delivered is nothing but receiving end voltage, that is receiving end side power, output power is given by VR IR cos phi r. So losses in output power is I square r. So that with the help of these two, we can get the sending end power is nothing but input power is given by, I'll write just here, input power is given by output power plus losses. Output power plus losses. So that input power is output power plus losses. Output power is nothing but power delivered, or you can say it as a receiving end power VR IR cos phi r. So that you can get here VR IR cos phi r plus I square. So with the help of this, you can get the transmission efficiency, that is power delivered to the power sent, that is receiving end divided by sending end power. So receiving end is VR IR cos phi r and sending end is output power plus line losses, that is nothing but VR IR cos phi r plus I square r. So next, to get the approximate expression for sending end voltage Vs, this can be obtained by changing some by doing some changes in the phasor diagram. So what and all the changes we'll be doing here, what I'll do for this particular phasor diagram, I'll just extend this line OA, then I'll draw a line perpendicular to the B with the help of C, then I'll draw a line perpendicular with respect to B. By doing these changes, I will get the approximate. Look at the phasor diagram now. See, the same thing I have done. So I'll be giving this as a C and C phi r. These are equal, phi r and phi r. So here I can define now Vs equals to Vs. That is OC equals to OZ. The value of OC is same as the value of OZ. So that I can write OC equals to OZ is given by the OZ I can write as C here, OZ, O to A plus A to Z. So that I can write OA plus AZ. Again, this AG I can rewrite as AF plus FC. AF plus FC. So that I can get OA plus AF. FG is same as BG. This is same as this BPC. So that instead of FG I can write as BC. So again the same thing, OA plus AF plus BG. Here just observe OA is nothing but BR plus AF is nothing but the component. So this component is nothing but IR AF, that is equivalent to AB IR into cos IR velocity component plus BG is nothing but I into XL sin IR velocity component. Next, effect of load of factor on regulation and efficiency. So for this particular, you should remember that there are three types of load. One is inductive load, the second one is resistive load, and the third one is capacity load. Okay. So here, for the reason associated with economy, the transmission of electric power is done with three-phase system. So on the left side, whatever you are seeing, that is three-phase system. This is three-phase system, and this is your single-phase system. So this system is regraded as consisting of three single-phase units. See here, three single-phase units: R phase, Y phase, and B phase. Three single units. So have to rewrite this, which is having each wire transmitting is having 1/3 of the total power. So as our convenience, what we are going to do is we'll be converting this three-phase equivalent circuit diagram into single-phase equivalent diagram. So to convert that three-phase equivalent circuit diagram into single-phase equivalent circuit diagram, there is a condition that all the phases should be same, and the phase shift between each phase is 120 degree. Then only we can convert. So here only one phase is considered. See here, only one phase is considered, that is Vs, and also towards load only one phase is considered, that is Vr. So on the load also it should be balanced load. So if the load is balanced, then only we can convert three-phase equivalent circuit of load into a single phase balanced load, and it is having the phase voltage of the same. Okay. So now once you have this, now we'll be study the effect of load or factor on regulation and efficiency. So effect of regulation first we'll study. So here the effect of regulation, and this is formula for regulation, and the regulation formula is the same as your transformer as you studied in transformer and generator. So regulation is given by IR cos phi r plus I into XL sin phi r divided by VR. So here this plus sign is for lagging power factor and this minus sign is for leading power factor. So when the load power factor is lagging or unity, when the load power factor is lagging or unity or such leading that, so here IR cos phi r is greater than I into XL sin phi r for the lagging power factor. So then voltage regulation is positive. As you already done in lab as well, the power factor is positive for the lagging. That is, for lagging power factor regulation is positive. For leading power factor the regulation is negative. So as well the sign is also changes. Here in case of this lagging power factor regulation, so the VR and I, that is the receiving end voltage and current flows to the load, that is load current. So VR and I, the regulation of line increases with a decreasing power factor. We'll repeat. Voltage regulation of the lines increases with a decreasing power factor for lagging loads only. Similarly, if the power factor is leading, so I into XL sin pi r is greater than IR cos pi r, or else IR cos pi r is less than IXL sin pi r. So for this particular, here the regulation which is decreases with decrease in power, decreases with decrease in power. So this is about the regulation of short transmission line. So the same points here. So all the same 4 points whatever I told now. So the first point is when the load power factor is lagging or unity such that IR cos pi r is greater than I integral sin pi r. So for the lagging power factor, voltage regulation is positive. So here which indicates that the receiving end voltage VR is always less than the sending end voltage Vx. So that with decrease in power factor, in case of only lagging loads, the voltage regulation is increases for given values of VR into I. In case of leading loads, or in case of leading power factor, the voltage regulation of the line decreases with the decreasing power factor. At the same time, vice versa of the load power factor in leading, that is IR cos pi r is less than I into XL sin pi r, or else I into XL sin pi r is greater than IR cos pi r. It is not sin pi r. Correction, this is cos pi r. So three different phasor diagrams for three different load. The first diagram is for lagging load, current lags VR, and it is for unity, current is increased with IR. This is for leading, current leads VR at angle of phi r. Sorry for the distance. About the medium transmission line, we'll discuss in next session. Thank you guys. If you're having any doubt regarding this, please let me know. So I hope if you understand the concepts, do the practice, understand the derivation, then we can move for the next concept. Problems we'll discuss as early as possible.